Welcome back for round 3, the final session in our 3-part Machine Learning for Forensic Practitioners short course sponsored by NIST.
Okay, so third part of our 3-part Introduction to Machine Learning webinar series. As all the other times, this work's partially funded by NIST, and we have fabulous collaborators that at different universities, including Carnegie Mellon, Duke University, University of California, Irvine, Virginia, West Virginia, Pennsylvania, Swarthmore, and University of Nebraska-Lincoln. This is joint work. And again, Alicia and Jeff are going to hang out in the wings and answer questions. I will answer questions when they come up during the webinar or at the end. So what we have been doing, parts 1 and parts 2, we had the intro to what is machine learning. We have by now set up a really nice framework for evaluating different classifiers. We've talked about trees and random forests. So what we're going to do today is I want to go a little bit into how we actually interpret scores from any kind of machine learning model. I'll focus on the random forest just because, but it works for all other scores the same. And then we'll also go into neural networks and have a look at an application from outsole pattern recognition. So interpreting scores, in particularly likelihood ratio scores, I want to give you a way to look a little bit under the hood of our random forest application for bullet matching. So we've got an online app that you can play with to investigate the sensitivity of the model to some of the parameters and some of the choices that we have to make during the matching. Then we'll talk about neural networks and go deep with neural networks and apply them to outsole pattern recognition. So last time we were talking about random forests, and our application was random forests for matching or for assessing the similarity between land engraved areas. So we got a random forest score for that. We started by extracting a couple of features, and the idea with features is that a feature is supposed to distinguish between what's a match and what's a non-match. So it doesn't matter whether the feature is, so features are usually numeric variables. And one side of the feature is more related to a match. The other side of a feature is more related to a non-match. Smaller number of features help a bit with explainability. You might have seen that with our example of the MNIST digit classification. We're dealing with just 784 variables out of the box. And it's the value of knowing that variable 239 is important might not be the same as knowing in the random forest for the bullets application that the cross correlation function is influential, or that the number of matches is positively correlated with the similarity. So a smaller number of features usually helps, and usually we would like features to also be recognizable by practitioners, so they're motivated by practitioners use. So here, for example, you recognize the CMS, the consecutively matching Straya score. That goes back to Biasotti. And we're just trying to describe in the features some approaches that examiners might use in order to declare whether two lands from a bullet are matching or have enough similarity for an identification or not. So we've got these individual features, and we trained the random forest on the Hamby 252, on scans of the Hamby 252 bullets. So we trained the so for those bullets, we know ground truth, so we know which lands match to which other lands, and we get the random forest model. So now assume that we've got a new land-to-land match, or a new land-to-land comparison, I should say, and assume that the score is 91. So what does that mean now? What we're doing now, given that we've got our training data, and based on the training data, we can estimate these curves along the random forest score. So the orange curve is telling us how same source lands usually score in terms of the random forest. The gray curve shows us how different source lands compare in terms of the score. So we see that usually the orange values are further to the right, indicating that the scores are higher. So let's assume we've got this score of 0.91. We find that on our scale. And now we're switching to these likelihoods. So the likelihood is the value that each one of those orange and the red curves have in the value of 0.91. For the orange, that's easy to see. That's quite a high value. So it's close to 2.77. You might not realize, but there is actually also a gray score here. It's just a very, very small score. It's not quite 0. It's 1.6 times 10 to the negative 16. So it's above 0. And we need that because we want to divide the orange score by the gray score. And so we can't divide by 0. So we're not dividing by 0 here because the gray score is not actually 0. But it's very small. So as we divide by that score, we come up with a likelihood ratio score of something times 10 to the 16. So that's a very large value. And what this likelihood ratio means is it indicates how much more likely it is to observe a value of 0.91 when it's coming from a same source comparison as opposed to a different source comparison. So it's much more likely that a score of 0.91 comes from a same source comparison, which means that this score for sure supports an identification. So let's do the same thing again. So let's assume that we've got yet another comparison of two lands. We get a score of 0.69 and doing the same thing. So we take the density for the same source comparison. We take the density value, the likelihood value of the different source comparison. We divide those by each other, and we come up with a score of 13.4. So that's much smaller than the 10 to the 16, but it's still quite a lot bigger than 1. So it's still quite a lot more likely, 13.4 times more likely, that a score from 0.69 comes from a comparison of same source lands over a comparison of different source lands. So it still supports an identification. So what if we go further down? A value of 0.5 in this random forest score now means that we have a likelihood ratio of 0.43. That's the likelihood that a value of 0.5 comes from a same source compared to the likelihood of coming from a different source. That's 1.65. So that gives us a 1 in 4 chance, essentially, that same source that a score of 0.5 comes from a same source comparison rather than a different source comparison. So 1 in 4, 0.26 is the score, and that might result in an inconclusive result, because 1 in 4, we don't have enough evidence to go really either way. We don't want to support an elimination, but we also really can't support an identification. Okay, so this is how we can use these density curves, and that's how we can use the scores, which also means that it's really crucial to have good basic training data. So these random forest scores come from the training results, come from the training model. We've got results where we know ground truth. So we've got the scores from different source. We've got the scores from the same source. Only if these, only if the training data is a good sample of the general population can we actually make general comments and generalize the model to things that are outside the scope of the model. So it's really crucial to have a good representation of scores. And for firearms examination, we know that striations change with bullet type, so ammunition type, and the rifling in the different firearms manufacturers use. So we need a good representation of those. So here our training data comes all from the same type of ammunition and the same firearms. So you all know the Hambi sets come from Ruger's P85. So we've got 10 Ruger P85s that produced those 35 bullets that make up the set for Hambi 252, on which this model is trained. So now we can go and try to see whether the model is still valid if we move slightly outside the scope of the model. So here we've got examples from the Houston study. That study consisted of known and questioned bullets from various different Ruger P95 barrels. So here we just have a comparison of 5 barrels where we have 3 test fires each. So those are barrels known F, known G, H, I, and J. Those are these columns of of scores or representation of scores on the left-hand side of the image. We've got 8 question bullets, unknown 27 through unknown 45. And what we're doing here is we're actually summarizing the random forest score across all 6 lands of each bullet. We're picking the 6 best matching scans of each bullet to bullet comparison. And what you can see here is that let's pick the first example. So for known barrel, for the 3 bullets shot from barrel F, we see that unknown 27 is matching to each one of the 3 bullets with a score of at least 0.5 or maybe 0.6 or so. Those are the orange scores. And it is U27 is not matching to any of the other known bullets from known barrels, nor does U27 match to any of the other unknown bullets. So what so this is how we can read this particular example. What you can see is that KH has a column that's completely gray. That means that there was no unknown bullet that matched to known barrel H. What we also see is that the last 2 columns, last 2 rows in this image, U14 and U45, do not match to any of the known barrels. So none of the bullets from any of the known barrels was found to be a match to bullets U14 and U45, but they do match each other. So you can see that at because the orange squares that correspond to U45 and U14 are both showing a nice saturated orange. You might notice that there are frames around some of the squares. So some of those squares have an orange frame. Whenever there is an orange frame around one of the squares, this indicates that these were, after we did the algorithm, we sent the scores to Houston, and Houston revealed to us the ground truth of the study. So we are visualizing ground truth here as the same by using the frame. So what we see is that ground truth supports what our algorithm would have told us in terms of identifications or not. So even though the algorithm was only trained on Ruger P85s, this serves as some indication, not as a final proof, but as some indication that we might be able to use this random forest to go beyond just the Ruger P85s. So in the future, obviously we want to refit the random forest to include more bullets and to include more combinations of ammunition types and firearm types and rifling types. And that's really where we need the community. So please send us samples if you have samples for test fires in the lab. If you're if you know of any studies that would benefit from 3D scans, we're always happy to come up with 3D scans and send them out to the community, as long as we can also use them to fit our random forest a bit better. Okay, so this is as much as I want to talk about the random forest right now. Anthony, I think there is a question in the Q&A, 2 questions in the Q&A sections. And okay, let me just get out. That way I can get my mouse back and I can check. There we go.
Sorry, I didn't know if you wanted me to read those to you.
Yeah. Is there a scale that shows which score falls into which category? There are scales. Thompson from UCI has given various scales of support. So yes, there are scales. I haven't been using them here though. For the Houston study, any background on why only 3 bullets were used for the test fires? Would more test fires affect the random forest values? And there is some variability between different bullets for the, so KF, yeah. Some bullets match better to U-27 than others. So the second bullet in KF doesn't match as nicely to U-27 as bullet 3 or bullet 1. So there is some variability. I absolutely agree. So the reason why there are 3, the reason why there are 3 test fires is just that the study was set up that way. So each piece consisted of 3 test fires for 5 barrels, and then 8 question bullets. So that's just the setup of the study. We actually do have more test fires from each one of these barrels, but that's outside of this particular study. So we can investigate the question, how many more test fires we would need to come up with better precision. We do have a student working on this question, and you are absolutely right. More test fires mean higher precision, but at the same time, we also would like for this to be implementable in a lab. And usually I think protocol is that there's going to be 2 or 3 test fires to see whether a confiscated firearm is marking or not. So we would like to use these fired bullets to establish whether they are marking and then compare those to unknown bullets. So we're trying to follow in the studies the setup that we typically see in the lab. Anthony, there is yet another question in the Q&A. Would you mind reading this to me?
No problem. This one says a follow-up, or is a follow-up, excuse me. How do you determine in your example that 0.26 is inconclusive?
0.26. That's a good question. At the moment, we don't have hard cutoffs, but so generally 1 in 4 is not being considered a elimination or a 1 in 4 is not considered to be a evidence in either supporting match or elimination. So generally weak evidence starts around 10 and 0.1. So 1 in 10 would be a better way to go here. And there's more follow-up questions. Anthony?
would 0.51 still be inconclusive?
0.51. 0.5, so 0.51 should be inconclusive, yes. So it's much more evidence, so it's smaller evidence. So if we have a look at the likelihood ratio here, 0.51. Oh, okay. I think I can see where this is going. So you might have noticed that here I'm calling the random forest results random forest scores rather than random forest probabilities. So generally, oftentimes random forests are being, the scores from random forests are being called probabilities. The problem that we have here with that is we do not want to call the random forest scores probabilities, because at that point it is far too easy to confuse these probabilities with random match probabilities. So the probability that we have two bullets, we have just two bullets that are just floating around somewhere in the world and they match. The probability for that would be the random, the probability that they come from the same source. That's the random match probability. No, that the random match probability is when we assume that they are coincidental matches. So that probability should be very, very, very small. Here we're looking at scores from the random forest that are, so you can see that 0.5, way more than half of the area is actually larger than 0.5. We do know that we have an imbalance in the class weights. So that together with the fact that we don't completely know how new ammunition and how new types of bullets, so just new data is relating to the random forest, to the random forest scores that we get from training. We don't know yet what we should be using as a random forest cutoff. So that's why we do not use a hard cutoff for the random forest score itself. So 0.5, so 0.5 is compared as a random forest score is compared. We are comparing the likelihood for same source to the likelihood for different source. And because that is a 1 in 4, so out of 4 bullets or out of 4 comparisons that result in a score of 0.5, 1 comes from the same source while 3 come from different sources. So at that point, we don't have enough evidence to make a decision in either way. Does that make more sense? So we would need to push the point at which we come up with differences further out. So I'm pretty certain that by the time that we are at 0.3 or so, we know that there's at least 9 different source comparison when we have one same source comparison.
Marissa, thanks you.
Okay. So let's go to the app that I promised. So this app is available really available, and I can put it into the chat. So I think, chat's disabled. I think I can use it, but you can only read it. Okay, so this app has a couple of pre-filled X3P files. So remember, those X3P files are scans from confocal light microscopes. It's possible to upload your own image if you want to. So for now, we've chosen 2 lands. These are both, again, from HAMBI sets, and I believe that this is HAMBI 173, but I'm not completely sure. So we've got 2 bullets. Bullet 1, land 5 is one of these. Bullet 2, land 1 is the other one. And just by inspecting those striation marks on either one of the bullets, you might be able to see that these look very similar. It would be nice if we could just flip one and use this similar to a comparison microscope, but please stay with us until we are actually able to do these kind of things. So this app allows us 2 different modes. There's the step-by-step mode. There's also the easy mode where we just hit the button, confirm lands, and the app will calculate different things. So you can see the progress down here, and you can see how things are working. Usually the speed's a little bit faster, but whenever I'm on Zoom, my computer doesn't like me as much. So but I think we're done. So there's a couple of steps, stage 1 through stage 6. And we just ran through the defaults of each one of those stages. So these are the defaults that the app is suggesting and the algorithm is suggesting. And in the process of going through these steps, a report is being created. So the random forest score here is a 0.99. And this is based on a value of, so I hope that you can recognize the names of these features. So cross-correlation function is regarded as the most important piece here. Cross-correlation is quite high at 0.87 and contributes to this overall very high score of 0.99. So this is the overall result of the feature evaluation. Below this, we can go through each step and look at what the algorithm has done. So in the first step, the grooves are identified and removed, and you can see here these blue lines are being found automatically. Then we fit these curvatures and switch to signatures. There's a smoothing factor that goes into here. So we could make this a lot smoother, confirm that, and that will reevaluate the process below. I think it's already done. So the changes, I think it might have actually changed a little bit. You might see the most in the changes in the way that these functions look like. So here we've got this double peak that has the broken peak, whereas here we've got this double peak that is actually a second peak. Okay, so then we're aligning these signatures. You can see how these are aligned. We extract these are that's a very strong smoothing factor that I'm using here. Maybe this is not quite what I want. Here we go. This is where the smoothing factor comes in. So you can see here there's a lot more peaks and valleys that are being recognized and aligned. And then the corresponding features are being extracted. So you can go into this app and see what each of these features does, what is particularly important for the algorithm to work is a proper cutoff of the grooves on the side. So let's assume that the groove is not being recognized properly. We confirm the boundary, and obviously here this is the wrong boundary, and sometimes the algorithm messes up and doesn't find a good boundary. So that's why we're showing each of these steps so that we can get the human in the middle of the algorithm and make changes as necessary.
Could you just clarify quickly, is the 0.99 an average?
The 0.99 is the random forest score for this particular comparison of those two lands. So that would be a very, very high score. So it doesn't take all of the other lands into account. So most likely the other lands aren't quite that nice. We can have a look at that by changing. So if bullet 1.5 is matching to 2.1, then 2.2 should match to 1.6. Let's confirm those lands and see whether these two lands match as nicely. And now the computer is working hard to refit things. And I told you, sometimes the computer is messing up. So here the boundaries are actually off. So let's move the boundaries in. So that's a better boundary, confirm boundaries. I could go out a little bit further here for bullet 2, but I don't think that I really have to. And you can see how these two lands are not nearly, these two signatures are not nearly as nice and as similar as the previous ones were. And that alignment is terrible. So here the overall score is a lot lower. So this is one of these matches that looks a lot more like a non-match. Let's see. Oh, yeah, when we have a look at this bullet, you can see that this land looks very nice. And this land, this bullet must have scraped the tank a little bit after it was being fired. So you can see that there's some tank rash here going over. So this bullet is deformed. So it's no wonder that we can't properly align this. But if we pick something here in the middle, we might be able to pull out a bit more of a comparison, but we would expect that this comparison is not nearly as good as the other comparison was. So let's see whether we can actually get that. So this, let's go back to stage 0 and try to identify coordinates. So you can, I shouldn't get carried away and try to make matches here. All of you are much more qualified than me making matches between lands and bullets. But what this tool allows us is to actually try out this algorithm while at the same time looking at images that hopefully look a bit familiar. And you can see here in this view, we can actually see stria. So if we're able to take a crosscut across here, we might be able to and even though there is a lot of deformation going on. Okay, so let's head back to the slides. So this app is freely available. It's a collaboration between CSAFE and OAITI. So this is a nonprofit part of Omni Analytics. Eric Hare is the chief scientist at Omni Analytics. And you might recognize the name Hare from the paper on the random forest matching publication. So this is the same Eric Hare that used to be a student at CSAFE before he graduated in 2017, a while ago. So we can get these step-by-step instructions. We can get an overall downloadable report. So once you're done, you can just print the HTML page and all of the parameters are being reported. So when you then come back and you include the same parameters, you will get the exact same result. So there's also some reproducibility guaranteed when you're using the same random forest here. Okay, so let's switch to neural networks. So neural networks are actually really, really old. So in 1944, neural networks were suggested by McCullough and Pitts, two cognitive scientists who were looking at trying to explain how the brain works. So neural networks have always had this idea of trying to explain how we process information, how we can come up with results, because we get input and we can come to conclusions. So McCullough and Pitts showed that neural nets can, in principle, calculate any kind of function. So a couple years later, a decade later, Rosenblatt in 1957 came up with the first trainable neural net, so the perceptron. And the perceptron consisted of just a single neuron. So you can imagine a single nerve cell that gets input and produces some output. In 1969, Minsky and Papert together essentially managed to kill the whole area of neural network before it was being revived, because they were showing that the execution time for very common computations for neural networks were at the time impractically time consuming. So the computational power in 1969 just wasn't there yet. So by 1980, in 1980, neural networks saw a revival. Smart algorithms were there to remove some of the limitations, and computers were also faster. So some of the limitations were removed, and that allowed some networks to being fit. So networks with just a handful of perceptrons, and but very limited. The very recent revival and the interest in neural networks has essentially started in maybe 2015. You can see on the right-hand side just the number of publications that we see each year in neural networks. So these are just publications that have as one of their keywords neural networks. And you can see that by 2018, the number is well above 10,000. So there's more than 3 papers a day that we would need to read to be completely up to speed in the area. So there's a huge growth, a huge recent growth in the number of publications and the research that's happening in neural networks. And that is all due to the modern graphics processing units, so GPUs, that allow us to actually fit complicated networks on just regular computers, and high-end clusters allow us to fit much more complicated, much more complex neural networks. So what is a neural network? So you can think of a neural network as a structure that has an input layer. So on the left-hand side, the greenish dots, that's the input layer. So that's where our training data comes in. On the right-hand side, the blue dots, that's our output layer. That's where the answers come out. And in between, we've got a pretty big, essentially black box of hidden layers. So those layers only talk to each other. And the first set of layers gets input from the input layer. The last hidden layer is talking to the output layer, and in between, the nodes are talking to each other. So there's some speculation on whether the brain works essentially like a neural network. The brain's computing power is much faster than anything that GPUs can do, but sometimes the training time is quite a bit longer. Kids need to be trained for years before they recognize different shapes and can name different objects with the right names. So that training process at least is very similar. So you can think of the input layer as the training data. And this training data comes with our labeled, so we know ground truth for the input layer. What we get out is a class for each label in the output. So each object that we want, or each class that we want to differentiate, has its separate node. So those layers in between, the hidden layers, consist of what's called neurons. So these nodes are called neurons. A neuron takes all of the inputs, multiplies the inputs with the edge weight. So each node has, each edge, so each line between two nodes has a weight. So each input is being multiplied by its weight. Each neuron sums up all of the inputs, uses an activation function, and then sends the output along to the next, downstream to the next node. So you can think of this as being, so the kind of activation functions that are being used are really almost 0-1 functions. So the kind of functions that are being used look a bit like this, like the sig mode or very often the ReLU at the bottom left function, where things are 0 until the node fires. So as if the node goes beyond a threshold, it's active and it's firing towards the downstream nodes. Beyond that, it will just dampen the input and essentially ignore the input. So most nodes at most times will ignore things. But once a node is being activated, it's firing downstream. So it has detected something and it is telling that to the layers downstream. That's conceptually what's going on. It leaves us with a ton more questions. So what's the right structure between input layer and output layer? Input layer and output layer are given, but what's going on in between is really, that's the question. So how many hidden layers should we include? How many nodes should each hidden layer include? Which activation function should we use? And then when we're actually checking whether the labels have anything to do with what the output layer is telling us each class should be for each observation, which loss function do we use? So how do we calculate the error? There's also different choices. So in terms of the structure, even neural network researchers call it the zoo. So here, meet the zoo. On the right, we've got an overview of some networks that are available. The colors indicate different functions. So all of the yellow colors are input nodes. All of the orange nodes are output nodes. You might see that there's extra symbols in some of these nodes. Those are additional functionalities that we can add. So my suggestion, start with a simple model and then try to add some complexity to the model. When we're trying to find a good model, what we need to massively use is the framework that we've introduced with the training data, the validation data, and then the testing framework. So that's essentially our only way to try to find a model that comes close to the data. So another piece that adds to the number of parameters. So at the top, we've got three layers. And generally, we start out with fully connected layers. So there is a node from each, there's an edge from each node in one layer to each of the other downstream, to each layer to each node in the next layer. There we go. So that's a fully connected layer. Each node has the parameter of when it starts to fire. So that those weights, that's a bias of the layer. Each edge also comes with a weight. So some edges are more important than other edges. And by default, we start with just random numbers on each of these edges, and we fit the network until we have weights that provide a better output. So that's a lot of parameters. In order to reduce the number of parameters and to help with overfitting, what we do is we randomly drop out some nodes. That's called the dropout rate. And that's something that is being added once in a while in a in the setup of the in the architecture of the network to help with overfitting. That adds another parameter. What should the dropout rate be? So here the dropout rate is a half for the first one and 1/2 for the second layer, and 0 for the last layer. Anthony, could you read me the question? Okay, let me.
Sorry, I'm struggling with my mute and unmute. The question says, is there two-way communication between the input layer, the hidden layer, and the output layer, or is communication always just in one direction?
That's a very good question. The communication does go back. That's called the back propagation. But the that is, let me get to that. Here. So the training is done in cycles. We start with random weights. We propagate that through. So that goes into just one direction. So input goes in, the weights are being multiplied, we get some output. Once we have the first iteration of output, we compare the output to the input and we adjust the weights. So that is how we go back to the initial. So there is some direction, there is some reverse propagation. So when we adjust the weights, we have a feedback loop. And then the question is, how often do we go through this feedback loop? We want to go often enough so that the weights reflect the data and the weights are learning from the data, but we don't want to overfit the network. And it's very easy to overfit. So yes, we go in both directions, but for right now, we're just focusing on one direction. And we're going to do an example. We are back to the question, which digit is it? And I realize that that's not quite the question that you would like to have answered, but it's a question that at the moment we can answer with the tools that we already have. So what we're going to do is we're going to take those images, we're feeding those through a set of layers, and you can see this is already a pretty complicated network. And that at the end, we're going to decide on whether this is a 0, 1 through a 9. So we've got 10 output values. So we're just doing the full classification in one go. We're not going to bother with, is this a 7 or not? We'll just go full force with this neural network from 0 to 9. So what is happening here is we're propagating the images through, and we're trying to pull out some information from where these values are black and where these values are white in order to distinguish between a 2 and say a 0. So the model that we're using here is a really, really simple model for a neural network. Not simple in terms of anything simple. Simple in the sense that we only have 5 layers. So we've got a dense layer followed by a dropout, another dense layer followed by a dropout, and then a last dense network. And the last dense network is just the probabilistic assessment of, is this a 0 as opposed to a 9? So that's why this has 10 values, 0 through 9 as the output. You can see that this simple network has 235,000 parameters. We have 60,000 images. You thought that 60,000 images were a lot. We have here 235,000 parameters. And one thing that you learn very early on in statistics is never try to fit more parameters than you have, than observations that you have. So we're violating this massively in this model. So that's why we need to keep a very good eye on not overfitting. It's terribly easy to overfit. So what we're doing is this. So, and I'm actually going to show this in R. So I'm using R 4.13, and the packages that I'm using for deep learning is Keras and TensorFlow. So you might recognize those from this Python packages with the same name. So what we're doing is we set up this model of our images, and we have 4 hidden layers, a dense and a dropout layer, a combination of a dense and a dropout layer. And then the last layer, that's just our output layer. And we're using dropout rates 40%. So we're dropping 40% of the first set and 30% at random in the second set. And we're going through this training in cycles, where we start with weights, randomly, we get our errors, we adjust our weights, and that adjustment is called how much do we learn? So what's the learning rate? And once we've adjusted the weights, we go back to 2, so it means we calculate our output again, and that allows us to get more errors. So we evaluate the loss function. Okay, let's see whether my computer likes me and allows me to do this. So here, I've got the NIST data set in my setup here. Here is the model. I'm setting up a model here, and I'm specifying the model architecture. And now I'm going to here, what we're setting up is as the loss function, we want to set up cross entropy, because our output is a categorical variable. It's a classification of an image into 1 of 10 different digits. We're going to use RMS, root mean square error, for our evaluation. And the learning rate is very small. We're going to adjust our weights very, very carefully so that we're not moving the model too much in one go. So we're setting up this model. And now we're going to go ahead and train our model. So we've got our images as the training data. We've got our labels as Y are our labels. So Y looks like this. We've got 10 columns, 1 for each digit. So these are all the zeros. So the second value here is a 0. The 4th value is a 1. 6th value is a 2. So you can see that in each row we only have 1 1. The 1 is the one that is the correct number. So this is called dummy encoding. I'll get back to that. We're going to just run 30 cycles, and we're going to use 80% of the training data as actual data, training data, and we'll reserve 20% of the data as validation data. So let's get going. And what's going to happen is we're running these epochs. And you can see that after each epoch, we get the output shown here on the right-hand side. So you can see how the model is being trained. The bottom is accuracy. The top is loss. So we want the loss to be minimized, and we want the accuracy to be maximized, hopefully all the way to 1, but it doesn't look like we're going to get there. So we already started out pretty high at 0.88. And you can see that we've got 2 lines, a green line and a blue line in each one of these windows. The green line, the blue line is the training data. So we start out quite low. The green line is for the validation. So you can see how the validation data is pretty flat, and at around 12 epochs, the validation is being the same as the training data. So that means that the training data, the model is starting to overfit in terms of accuracy at just 12 epochs. And then you can see as we repeat the process more and more, so we tighten the weights more and more, we learn more, the weights are getting closer to the actual, to the training data. So you can see that they are getting a bit too close to the training data. So here the loss in the training data goes down, but the loss in the validation is starting to go back up. So you can see here the loss in the validation set after 30 epochs is about 13%, and it was below 10% earlier on. So it would have been better to just already stop at this point, to stop much earlier, maybe here, with losses under 10% for both validation and training. So we can already get some hints as to how the model is doing by looking at the comparison between training and validation data. Our final evaluation is actually the model evaluated on the test data. So we kept that back. So for the test loss, we've got a 10% loss, which is actually quite a bit better than the 13% from the validation. So our test is somewhere here in the middle. And the test accuracy is at 0.98, which is, again, somewhere between the validation and the training. So our test data is closer to the training data than our validation data was. So this is nice confirmation. And you can see here, this is also nice to see with the interactive feedback that we're getting here. What would be, so you can see that we're making all kinds of decisions. So we've decided on the architecture here. We've got two of these dense layers. We've got a decision for the dropout. So we're overfitting fairly quickly. So it might be nice to increase the dropout rate a bit from maybe 30% to 35%. And actually what I want to do is I want to add another layer. So we're just changing the architecture, and the way that you change is just trying to make small changes and see whether those small changes nudge the model into the right direction. So let's do 64 units before we go all the way down to 10. We refit the model, so I'm deleting the original model. I'm setting up this new model with the new architecture. So you can see that the architecture is now a little bit more complicated. We've got, yeah, we've just added another 8,000 parameters to the model, but we're also using a bit more dropout. So it might, so we might see the same amount of overfitting because we've added more parameters. We might be able to reduce the overfitting a bit because we've added the dropout. It's not really clear in which way this is going to go. But the nice thing is we can just reevaluate this. So the model is now going to run again. And maybe you've seen this before. In the previous setting, each evaluation took about 1 second. Because we've added complexity to the model, now the evaluation is taking us already 2 seconds. And you might be able to see that this is going to add up quite quickly as when we're adding more nodes, more layers for this additional complexity. We okay, so the jury is in. We actually know how this is panning out. Overfitting is not nearly as much of a problem as it was before. So you can see how both training and validation accuracy is very similar. Same with the loss. So it seems that in terms of overfitting, we went into the right direction. But what we see is that at the same time, overall, the accuracy has gone down a bit. So now we're at 0.79. Before that, we were at 0.98. And you can see that we're here really fighting for every 10th of a point, sometimes even to 1,000th of a point. But this might have been a step in the right direction. You can see here test loss. Oh, that's a little bit higher than before. Test accuracy is a little bit lower. So I'm not quite that confident that it was a step in the right direction. But these are the kind of decisions that you're making as you're fitting and refitting these neural networks. So let's get back to the presentation. So when do we stop? When we've got a good model. So how do we evaluate these models? So I already talked about dummy encoding before. So we can assume that we've got labeled input, and let's just assume that this is the labeled input. So 72104. So this is different from what I was showing you before, but we've got labeled input that's transformed to a dummy matrix. So again, each row has a single one, and the column corresponds to the values from 0 to 9. So the first input is a 7, so column number 8 has a 1 in the first row. Column number 3 has a 1 in the second row, and so on. So that's our dummy matrix. So each column is a 0, 1 vector. So column 1 contains ones for all of the zero images. So now we fit our neural network, and that spits out a result. So we get predictions back. And this is what the predictions look like. So these are the actual predictions from the neural network that we just fit, the first one. And you can see that these are really good, at least for the first 10 digits, for the first 10 images. So we are very, very close to, in our predictions, to what we were. Our predictions are very close to the actual data. There's a little bit of a uncertainty of whether image number 8 is a 4 or a 10. There's a little bit, so a 1% chance that it might be a 4, but a 99% chance that it's a 9. So the overall error rate for the neural network that we fit is 1.9%. We can compare that to the error from the random forest. And the error from the random forest is for the full random forest. So we can run a random forest for all 10 digits. With 50 trees, we get an error rate. So the out of bag error, so that's like the validation, like the error on the validation set, is 4.15. The actual test error for that random forest is 3.2%. So the out of bag estimate overestimates the test error a bit. But overall, the test error is from the random forest is more than 1 percentage point higher than the neural network. So here is a confusion matrix of the random forest for the random forest on the test set. So you can see that we have very strong support on the diagonal. So 98.1% of the cases are good. And then we've got, oh no, not 98. Okay, sorry. 100 minus 3.2, whatever that gives, 96.8, right? So 96.8% of the cases are good. We do see that some distinctions are a little bit worse than others. So for example, we've got this 20 in the third row. That's class 7. So is it a 7 or is it a 2? 22s were mistaken. So no, 27s were mistaken for 2s in the prediction. Similarly, 25s were mistaken for 3s. So probably because the top line was cut off or not properly printed. So you can see how these kind of errors happen. And the worst, the model did the random forest did the worst for class 4. So 25 4s were actually predicted mistaken for 9s. And you can see how that might happen. So 25 4s were mistaken to be 9s. So how does the neural network do on exactly the same data? Here's the confusion matrix, and you can see that there's a lot of zeros suddenly in there. There's a few zeros for the random forest, but a lot more zeros for the neural network. There's also no problem with 4s versus 9s. That problem is solved in the one direction. It's a little bit harder for the neural network to distinguish 9s from 4s. So the inverse problem is now a little bit harder. But overall, you can see how those numbers are generally smaller than the random forest numbers. So what do we gain? Okay, and here are receiver operator characteristics curves. On the left, ROCs for the random forest. So there's 10 lines, one for each of the images, one for each of the digits, 0 to 9. And you can see that the random forest model is really good. You can see that the neural network is really good. The neural network is a little bit better than the random forest. So we're getting a little bit closer in the top left corner of the ROC curve. So we're closer to perfection for the neural network. So which one should we use, random forest or a neural network? So the two share a lot of advantages and a lot of disadvantages. So neural networks can deal with the same kind of data as random forests, so large amounts of data, multi-class classification, qualitative and quantitative variables. Non-linearity is not an issue for either one. They also share a disadvantage. Both random forests and neural networks are really hard to explain. So the question of how did you get to that usually results in us saying, well, the algorithm told us. So it's hard to diagnose these or hard to explain why. And that is going to, that's a massive research area. So there's more and more support trying to come up with approaches on making things more explainable. So if random forests and neural networks share so much, which one should we use? Neural networks or random forests? So most often neural networks can be trained to have a better performance. So there are usually, you can say that there are neural networks that perform better than a random forest. But at the same time, neural networks provide us with so many choices in terms of the architecture that finding the best model is an impossible task. It's already pretty hard to find a good model. So there's just so many choices, and as the complexity of the model increases, usually the performance also increases with that. But at the same time, as the complexity of our model increases, the computational requirements also dramatically increase. So sometimes it's just a trade-off of, yes, we can get to a model that is better than a random forest, but at what cost? So what additional costs? So how much more resources do we need to invest to come up with a model that's actually better than the random forest? But if we want to, if we need to, then the neural networks will come up with or there will be a neural network that shows better performance, as long as we have enough data. So neural networks need vast amounts of training data because there's such vast amounts of parameters. So we have to consider these kind of trade-offs. So let me, let me go into deep neural networks. So deep neural networks are essentially just very complex neural networks. And you can think of these deep neural networks as having applications in what we would consider artificial intelligence. So image classification, here's an example. The input is an image and the output is just an object. So this, these kind of deep neural networks are good at just identifying what is shown in an image. So that's what Google uses when you show it the picture of a flower, and Google doesn't only recognize that it's a flower, but it will also tell you what kind of flower it is. So that's what's behind that technique. Deep neural networks that is being trained and constantly being improved upon. So image classification, face recognition, road recognition, so anything that's around self-driving cars, all of that is done using deep neural networks. So one way to get around the parameter requirements or the training requirements is to use pre-trained features. So you can see that the deep neural network has a feature learning side and then the classification side. Generally, we call the classification side on the right the head of the neural network. So what we're doing is we can take the head and train just the head and use a pre-trained set of features and reuse that for similar problems. So that's what Susan Vanderplas and Rick did in their in this application here. So the idea is we want to use deep neural networks to recognize different shoe sole patterns. So let me back up. So this is not my research at all. This is all Susan's doing. So Susan is the statistician on the project and Rick is the engineer on the project. So the idea is that what we want to do is we have two shoe prints. We want to be able to say whether the left shoe print was made by the same shoe as the right shoe print. So do these two prints come from the same shoe? As we're trying to answer that question, what we also need to answer is what's the possibility that these two shoes just coincidentally match? So what's the probability that they just happen to match, but they're really from different sources? And that is part of answering that question is trying to know your local population. So how many people wear these type of shoes? So where were these shoe prints found? What kind of weather was it? So those kind of shoe prints are probably a lot more common in an outdoorsy setting than indoorsy, but so we need to know where these, we need to know more. So what's the local population? So how can we characterize the population? And what kind of problems do we have when we're trying to characterize the population? Number one is there is no database of all possible shoes. So there's so many different variables like manufacturers, different models, sizes, what kind of thread style or what kind of manufacturing molds, all of this constantly changes. There's also the difference between what shoes people purchase and what shoes people wear. So there's definitely dressy shoes that I have in my, that I have at home that my husband complains about, that I don't actually wear. And then I've got my trusted sneakers that I wear everywhere. So I'm pretty sure that we all have these kind of shoes. So some shoes are just for special occasions. So we have to distinguish between which shoes we wear and which shoes we purchase. Then also local populations differ wildly. So there's very different shoe patterns that we're going to find in, let's say, a national park compared to a mall or compared to a conference. So local population depend on the environment. Additionally, everything keeps changing, so new tread patterns appear very frequently. And so let's have a look at what kind of features we should keep track of. So here we've got 3 shoes. The only difference between these 3 shoes is the size in which they're being sold. The make is the same, the model is the same. The type of the shoe is the same, but obviously you can see that the tread pattern is quite different. It's a different different molds are being used, but generally it's a similar-ish pattern. So we might be able to recognize the make and model based on these different sizes. But in order to say whether this exact same shoe was made, the exact same shoe made an impression, you can see that these relevant features are not going to tell us that yet. So we can't use these relevant features to identify an individual, but what we can do is we can, they are subclass characteristics. So we can use different subclass characteristics to exclude. So sometimes you see one shoe pattern and it's very similar to brand shoe patterns. So here are 3 shoes that have all very similar tread patterns. They just come at different costs. So there's very similar styles across different brands. And what we can do is we can already, while we can't actually get the exact make and model, we might get close and we might be able to just get a good subpopulation based on recognizing individual features. So how do we get what do we want to do? So essentially, we want to assemble a database of shoe images. So we want to have a training data that has shoes from the local population where we have identified features so that we can actually calculate a random match probability. And eventually, so the further down we go in this list, the more wishful thinking comes up. So eventually we want to have some probabilistic comparisons. So that might get us towards more individual features. So how do we get data? This is where Rick comes in. So you can see here the shoe scanner. CSAVE showed this scanner also at IAI and in other places. So find us on at conferences and then walk over the shoe scanner. So it's this elevated ramp. At the top is a plexiglass plate. You step on that plate and an image is taken from the bottom up to capture your shoe sole. So these shoe soles are then, we want to identify features in these shoe sole patterns. So, and we want to do this automatically. What we also want is for this to be robust versus lighting conditions. So whether it's very early in the morning or the sun's out, that shouldn't matter. The exact rotation of the image of the shoe should not matter. The image quality hopefully also doesn't matter, but it's going to come in. And then tread colors are also supposed to not matter. So on the right here, you can see 4 different shoes, 4 different bottoms of shoes. And they all have the same tread pattern, but the colors are very different. And for me, at least, it's really hard to tell that the second and the 4th pattern are the same as the 1st and the 3rd. But we want the algorithm to be able to just overlook the colors because the colors don't feature when we get just a shoe print. We also want to have features that use human-friendly terms so that we can recognize the features afterwards. So here is a set of features. So this is a set of features that Susan decided on when she started training these shoes. So we've got 3 examples for each one of these 9 different features. So bow ties, you recognize the famous Birkenstocks as the first example. lots of shoes have lines, stars, we've got polygons, and then depending on the number of edges, we've got triangles, quadrilaterals, and then polygons. So anything that has more than 4 edges goes into the polygon category. And then there's so much text on shoes. So there's a category just for text. So we start, when we get shoes, or when we try to learn, we need labeled data. So we need to know ground truth. So how do we get ground truth besides looking at the shoe? We have people look at shoes and describe what they see in words, ideally also by drawing the area where they see particular pieces. So here is a screenshot of the Label Me app. We're paying undergraduates and graduate students to go through and label shoes. So there's about 28,000 labeled shoes in the database, and this looks again like enormous amounts. But remember, we have so many parameters. So here is, you can see the idea is we have a shoe image going into the neural network, and then we start this process. And at the end, we've got the output that tells us which features are shown on a particular shoe sole. So we're starting the feature detection process. So in this model, we have just in the base 14.5 million parameters for the model head, and the simplest possible model head that we have for 9 output classes in this situation. We have more than 8 million parameters. So this gives us a parameter space of about, just over 20 million parameters. So if we try to fit a model like this, that's shown here, we need about 2 to 3 weeks with 4 high-powered GPUs. We also need more than 1 million labeled images. And at the moment, there's about 28,000 labeled images. So we're just about 1 million short of the 1 million. So there's only a dent in the labeling that would be needed to completely fit this full convolutional neural network. So what we do instead is, what Susan does instead is to use a pre-trained base. So the pre-trained base, essentially what we do is we take the model head and we only keep the model head, and we switch out all of the weights from a different source, and we start from there. So the pre-trained model that is being used here is the VGG16. That's a pre-trained convolutional neural network that's trained on more than 1 million images from ImageNet, and essentially focuses on trying to tell the difference between a frog, a car, and a train. So it's images, but it's using a lot of similar features to what we're looking for in the shoe patterns. And there's a question in the chat. Oh, I'm sorry, Anthony. Yes, I'm not going to put any pressure on Anthony by pointing out that he's not in his office right now. So there's so we're switching out the base of the convolutional network by this pre-trained model VGG16, And what that means is we are only needing the 8 million parameter. We need to fit the 8 million parameters from the model head. And the nice thing is that can be done in about 3 hours. So it's a much simpler structure. Having 28,000 images available to us is enough to fit those 8 million parameters because the structure is a lot simpler. So this is what the overall model looks like. This is the performance. So on the diagonal, we want to see high numbers. So we want to be able to say that if we predict a triangle, the image actually also has a triangle. That value is 0.74 here. So that's a 3 and 4 that when we say a triangle, it actually is a triangle. That's much better than if we just randomly guess. We have a 1 in 9 chance to get things right. Off the diagonal, so in the top left corner and the bottom right corner of that matrix, we want to have as low values as possible. So that's the error that we make. So this 0.15 that we see in the top left square, that is where the model said that it was a triangle, whereas in case it was actually a bow tie. So 0.15 is generally not a bad performance. So overall, the model is quite good. It has an accuracy of above 0.8, so 80% performance accuracy. Some categories are definitely harder to distinguish than others. So the worst one here is in the 4th row in the last column, 0.69. So that's all of the predictions that were made for a quadrilateral that were actually a triangle. So generally, the model has problems counting the outside of, or counting the number of corners of any of an object. So distinguishing between a triangle and a quadrilateral and a polygon is generally a hard task. So you can see how this is quite often messed up. So 0.67, that's in the middle here, the 5th entry in the quadrilateral. The model predicts a quadrilateral, but it is actually a polygon. So it has more than 4 corners. The model loves bow ties. So 0.85 is the accuracy for bow ties. That's overall the top category. Bow ties are easy to recognize, and it's not as hard to, and it's not as easy to separate a bow tie from anything else. So if the model says that it's a bow tie, the prediction accuracy is quite high. Some patterns are more frequent than other patterns. I just said that the model loves bow ties. Unfortunately, bow ties are not as often a feature on the bottom of shoes. But if they are, this model recognizes a bow tie when it sees one. Quadrilaterals are the most common feature, and unfortunately, quadrilaterals are also quite hard to distinguish from other features like triangles or polygons. Okay, so what does the model see? So here's just a couple of examples of what the model sees, and additionally overlaid where the model looks. So there's on top of the feature that the model sees here, there's this additional color in green and yellow. That means that there's high activity. So the higher, the more yellow. So that's where the model looks, and the yellow, that means a lot of the weights in that area were activated for this particular prediction. So the model sees the original image, and for a circle, you can see that the round shapes are activated. So the model sees a circle when we have these half circles. So the model is right. The model reacts to some circle shape, some round shape in its activation. Similarly, quadrilaterals are activated in the flat shapes of these half circles. So when there's a flat shape, quadrilaterals are speaking up and saying that here is weight for quadrilaterals. And you can see that the shoe labeler labeled this as a quadrilateral. And you can see that some of our labels are questionable. It could also, the shoe labeling could also point out that there are some circular feature or some round features in the shoe pattern here as well. But in the training data, this was marked as quadrilateral. So what else does the model see? The model sees a circle, 98.988. That's a really high activation out of 1. So activations are between 0 and 1. So circle is highly activated in this case, and you can see in the activation, the yellow is a circle. So the model is right. The modeler, however, or the scanner, the labeler, saw this text, Adidas, and labeled this as text. Both are right, but for right now, the circle would actually contribute to the error that the model makes, because this Adidas is not actually being labeled as a circle. So you can see that we are getting into a range where labeling is getting quite hard, because these are usually activities that the computer does so much better than human beings. Having human beings evaluate 28,000 labels of patterns is excruciating. And sometimes definitions are also not completely clear. The model has a very good point in saying that this is a circle. The labeler has a very good point in saying that this is text. What we need to agree on is that it can be both. The nice thing, the neural network does not have any problems with that. So we can just add to the training set that this is also a circle, is showing also a circle, and say that the model is right in this instance. Here we've got a diagnostic. It is marked as text. So, and we can see the S shape. The model is quite certain that this is a circle, and it finds the spiral shape of the S as the attraction. For the text, it's not completely clear what the model is focusing on. So it's generally the focus points are not very specific to the text. So sometimes the model will tell us or will decide on features without us being able to understand what the model was looking at when it made its decision. So is this a circle? Is this text? How wrong is the model? I still would like to think that the model is not completely wrong with the circle. It's definitely a circular shape, but it depends on the definition of what a circle is and what text is. So I'm pretty much at the end of my remarks. Oh, very good. And I only have 6 more minutes. Just a couple of last remarks, and I'm ending on the same slide that I ended on the last 2 times. I want to point out model limitations. So always keep in mind that any model is based, any machine learning model is learning. So it's based on training data, and that training data introduces a lot of limitations to the model. Sometimes the model is able to overcome some of the limitations. So some models can be correctly applied to situations that go beyond the training data. But it's not at all clear that that should be the case. So whenever a machine learning model is being used in practice, it has to come with limitations of where it can be applied, and it should really not be applied to anything outside of what is being validated for this particular model. So the generalizability is always one of the big issues of any kind of machine learning model. How reliable is this model when I'm using it on a particular data set? Another big issue is, how do we explain the results? And you've seen that the better the models are, the harder it becomes. Explaining a logistic regression can be done in statistical terms, where we know as this feature increases its value, the prediction is going to increase with it by this amount. As we get to better models or more accurate models, interpretability disappears, and the models become less and less explainable. For specific remarks for the neural networks, we've seen that deep neural networks need a lots of training data. But at the same time, good convolutional networks can also help us identify problems with the training data. So we can actually use these convolutional neural networks and apply and find training data problems with the training data. So just that helps us weed out bad examples. Our training data can always be as perfect as we want the data to be, so that we're not distracting the neural network from by introducing human errors, because otherwise, if we train the model until the computer also captures all the human mistakes, human features, making mistakes in particular situations, then the computer isn't any better than a human. It might be faster, but what we really want is a model that might even outperform people when it's doing very, very silly, simple tasks. So these kind of models are not meant to replace anybody. It's not these models are not supposed to replace practitioners, examiners. They're supposed to support practitioners and examiners. And for that, they need to have their own value. So having a faulty colleague in here is not going to be helpful. So we need to watch out for these model limitations and generalizability. So before we get to questions, thank you very much for sticking it out with me for 6 hours. I know that this was a long time. I was there, I know. But we would really like to work with us. You just like I said, machine learning models need data, a lot of data, more data than we have access to. So please reach out to us. So anything that has to do with impressions and Straya, when you think that you would benefit, your study would benefit from having 3D scans, please contact me. If you've got any kind of general questions or you don't quite know who to contact, reach out to forensicstats.org under our contact, and we will figure out who the best person is going to be to reach out to you. Thank you so much, and I will take now questions. Okay, so here's a question from Jani. Is it not the brain's ability to deal with overfitting that make algorithms primitive yet complicated? Yes, so the question really is, how do we prevent overfitting? What I'm seeing in class is a lot that students go through stages of where they themselves overinterpret and overfit. I can only say that from statistics students. You might see that in training new firearms examiners or any kind of forensic practitioners, really, that they might overinterpret initially. So either identify or exclude a bit too quickly. So this kind of overfitting is something that I believe that we learn, that we're not going into extremes very quickly, because we've seen more extreme in our past. So in a way, algorithms can also benefit from their past. So if we expose algorithms to more extreme situations, they will also learn not to overfit. So I think computer scientists and cognitive scientists still argue whether the brain is or is not a neural network. So it's a very similar. People are convinced that it's a very similar situation, but our brain has so much computational power that it's leveraging that power a lot better than regular computers. Thank you so much. Please reach out to me for collaborations. And I hope that you enjoy the webinar series in the future. Thank you, everybody.
Dr. Hoffman, thank you as well for sharing all your insight and your experience. Thank you all for joining us. We hope you have a great day.